Today, we're going deep underground, right to the border of Switzerland and France, to a place where science fiction basically becomes reality. We are exploring the largest, most powerful, and just the most complex machine humanity has ever even tried to build, the Large Hadron Collider.
Okay, let's just let that sink in for a second. This one sentence, it just perfectly captures the mind-bending ambition of the LHC. See, it's not just a machine, it's a time machine. It's designed to let us peek back at the very first moments of our entire universe.
So, what do you need to build a time machine like this? Well, let's start with the almost absurd physical scale of this thing. We're talking about a true scientific giant. First off, you need a racetrack for particles. And the LHC's main ring is a 27-kilometer tunnel. That's big enough to circle a small city, and it's buried deep underground to shield it from any background radiation. Now, to steer these particles, you need over 9,000 incredibly powerful superconducting magnets. And to get them to work, you have to cool them down to minus 271.3 degrees Celsius. To put that in perspective, that is literally colder than the vacuum of deep space. Inside this incredibly frigid tunnel, beams of protons are accelerated until they are moving at 99.99991% of the speed of light. We're talking just a hair slower than the ultimate cosmic speed limit. And then this is where the magic happens. These beams, they're traveling in opposite directions, and they're smashed into each other with unbelievable precision, creating collisions over 11,000 times every single second. So what are we actually colliding here? Well, that's the H in LHC, hadron. Hadrons are subatomic particles, like the protons and neutrons that make up the nucleus of every single atom in your body. And the C, that stands for collider. And it's actually a pretty elegant solution, right? Instead of just hitting a stationary target, you smash two beams together head-on. Why? To create the highest possible energy in that impact. But honestly, beyond the physics, there's the human scale of it all. This isn't the work of just one country or one lab. It is a monumental collaboration of 10,000 minds from all over the planet, all focused on this one incredible machine. All of this insane engineering, it all begs one fundamental question. Why? Why go to all this trouble? Because the LHC is our sharpest tool for probing the deepest questions we have about the nature of reality itself. Questions, just like this one. It sounds almost philosophical, doesn't it? But it's a profound physics problem. Why do particles have mass? Why isn't the universe just this thin soup of light and energy? Why is there, stuff? Answering that why was right at the top of the LHC's to-do list, which, let's be honest, reads like something out of a sci-fi novel. It was built to find the Higgs boson, to search for the invisible dark matter that holds galaxies together, to look for supersymmetry, a theory that says every particle has a hidden partner, and even to test for the existence of extra dimensions. And that brings us to the LHC's most famous success story, the hunt for a particle so important it was the final, missing piece of our best theory of particle physics, something we call the Standard Model. To really get why this is so important, you have to understand that the Higgs boson isn't just another particle. It's the physical proof of a universal energy field, the Higgs field. Think of it like this. As other particles move through this field, they get a kind of cosmic drag, and that's what we experience as mass. Without it, they'd all just zip around at the speed of light, and atoms, stars, and, you would never have formed. This timeline just shows the incredible patience of science. The idea was first proposed way back in 1964. It took nearly half a century of brilliant work before the LHC was finally powerful enough to even test it. And then, on July 4th, 2012, the world got the news. They'd found it. But here's the thing. Finding the Higgs wasn't the end of the story. Not even close. It was really the end of one chapter and the beginning of a whole new one. The LHC's work is far, far from over. You see, science is a process of discovery, and that includes discovering what isn't there. Of course, the LHC has made incredible finds, like confirming a state of matter called quark-gluon plasma and discovering 59 new types of those hadrons we mentioned. But so far, it has found zero evidence for some really popular theories, like supersymmetry or extra dimensions. And that's just as important. A null result tells physicists where not to look, and that forces them to go back to the drawing board and rethink their biggest ideas. So, what's next? The high luminosity LHC. Think of it as a massive upgrade that's going to dramatically increase the number of collisions, basically creating a data tsunami. The whole goal is to collect 30 times more data, letting scientists hunt for incredibly rare events that just might hold the key to the next great breakthrough. When you really step back and think about it, the Large Hadron Collider is so much more than just a machine. It's a testament to human curiosity. You can think of it as a cathedral built not for worship but for questioning.
And its impact goes way beyond particle physics. I mean, to handle the unbelievable amount of data, physicists at CERN invented something to help them share information. You might have heard of it. It's called the World Wide Web. And that spirit of connection continues today with a global computing grid that links the entire planet.
So maybe the greatest discovery of the LHC wasn't a particle at all. Maybe it's a reminder that when people from every corner of the world come together, united by nothing more than a pure desire to understand the universe, they can achieve the impossible. And in our modern world, that is a discovery worth celebrating.